In this video we're going to talk about dynamic equilibrium. Now we've already spoken about reversible reactions, and a dynamic equilibrium is a very specific type of reversible reaction where both the forwards and the backwards reaction are occurring at the exact same time. So our definition is going to be a reversible reaction where both the forwards and backwards reactions occur at the same rate. That's really important. So they're both occurring at the same rate. So we established before that not all reactions are reversible. Some are, some aren't. And the same is true for dynamic equilibriums. Not all reversible reactions form an equilibrium. Some reversible reactions, like the two we looked at in the last lesson, they can either go forwards or backwards, but they can't do both at the same time. It's either forwards or backwards. Whereas in a dynamic equilibrium system, you've got both of those reactions happening at the exact same time at the exact same rate. And what that means is that you would observe no change. If you were watching an equilibrium system that was set up in a conical flask, for example, it would appear to be doing nothing, because as quickly as the forward reaction is occurring, the backwards reaction would be occurring at the exact same time, so it would cancel it out. So you wouldn't see anything, you wouldn't see any change, you wouldn't see any color changes, you wouldn't see any bubbles, you wouldn't see any products being produced. It would appear to be doing nothing because it would be perfectly balanced between the two reactions. Now, another thing that is key to a dynamic equilibrium is it must be in a closed system. So it's a reversible reaction where both the forwards and backwards reactions occur at the same rate, but also it's in a closed system. And what we mean by a closed system is simply that none of the products or reactants can escape. So it must be, if we're talking about a conical flask, there must be a bung in the top preventing anything from escaping. So if we look at this setup down here, this is a closed system. Nothing can get in, nothing can escape. If you don't have a closed system, then you can't establish a dynamic equilibrium. So here is an experiment which ordinarily we would demonstrate for you, but obviously I'm not going to be able to do that. I have recorded a different dynamic equilibrium video, which will be at the end of this lesson that you can watch, demonstrating the fact that it is a dynamic equilibrium, demonstrating the fact that we can manipulate it so that it travels more in the forward direction or more in the backwards direction. But we can talk through this experiment still. So here we have a reaction between nitric acid and copper turnings. Okay, and what that does is it produces nitrogen dioxide gas, which is a toxic brown gas, which is why I couldn't film it to demonstrate for you, because it's quite toxic. And that forms a dynamic equilibrium with N2O4. Now, as long as this is in a closed system, we will get an equilibrium established between these two different nitrogen oxides. Now, this one here is a brown gas, but this one here is a colorless gas. Now, when it's in dynamic equilibrium, first of all, we can see its reversible reaction because of this double-headed arrow. And while it's in dynamic equilibrium, it would appear to be doing nothing. So it's going to be produced by the nitric acid reacting with the copper turning. So all of this here and collecting here in the gas syringe is going to be filled with this nitrogen dioxide gas. And when it establishes the dynamic equilibrium, remember it's going to be a mixture of both. There's going to be some NO2, there's going to be some N2O4. So what we're going to end up with is sort of a pale brown mixture of both. Now, it would appear to be doing nothing. If you were looking at it and you were looking in this gas syringe, you would just see a pale brown gas. But actually what's happening is NO2 molecules are forming N2O4 molecules, and at the exact same time, exact same rate, the N2O4 molecules are forming NO2 molecules. And both of those reactions are occurring at the exact same time, exact same rate. So it would appear nothing is happening. So what's interesting about a dynamic equilibrium system is that they don't want to change the conditions. So a dynamic equilibrium will resist any change in conditions. So if you were, for example, to change the temperature, the dynamic equilibrium would shift so that it could counteract that change. So for example, if I were to increase the temperature, the dynamic equilibrium would try to decrease the temperature. If I were to increase the pressure, it would try to decrease the pressure. They resist any change in conditions. So what we have here is the NO2 and the N2O4 is we can change the conditions and we can encourage the equilibrium to shift either to the right hand side and produce more of the colourless gas, which means that what we're looking at would go from being pale brown to colourless, or it could shift to the left and produce more NO2, which would mean more brown gas being produced, so it would go from a light brown to a dark brown. So because we've got quite a nice colour change between the left and right hand side of our equilibrium, we should be able to see quite visually when it is shifting to the left or the right. So I've said that dynamic equilibriums can shift to counteract the change in conditions. Now it all sounds quite complicated, and this topic is one of the tougher topics in the GCSE. But fundamentally all you need to know is that the equilibrium will shift to counteract the change. So whatever you're changing, the equilibrium will shift to counter it. So it will just try to achieve the opposite of what you're changing. And even though we could be talking about temperature or pressure or concentration, fundamentally the equilibrium can do one of two things. It can either shift to the left and produce more of what's on the left of the reaction, or it can shift to the right and produce more of what's on the right of the reaction. So we just need to work out how to predict which side will be favoured. So what we would have seen if we'd been able to see this demonstration is when the pressure was increased, what colour change would we see? So if we'd been able to watch this, it would have gone from pale brown to colourless. So by increasing the pressure, by pushing that syringe closed and increasing the pressure of our equilibrium, what we would have seen is the equilibrium mixture going from pale brown to colourless. And the fact that it's done that shows us that it is shifted to the right hand side, because on the right hand side we have the N2O4, which is colourless. Okay, so we'll add that in brackets. So it's shifted to the right hand side. And again, because we're talking about a reversible reaction, we need to move away from talking about reactants and products, because technically both sides are reactants and products depending on which direction you're going. If we're going left to right, then the NO2 is your reactant and your N2O4 is your product. But if we were going in the reverse direction, then the N2O4 is your reactant and the NO2 is your product. So instead of talking about reactants and products, we're going to talk about left-hand side and right-hand side. So we can see from this pale brown to colourless colour change, we can see that it's shifted to the right-hand side because the right-hand side is the colourless gas. So what direction must the position of equilibrium move in order to produce this colour change? So we've actually already answered that. It's moved to the right-hand side. If the plunger is pulled out to decrease the pressure, what would you expect the colour change to be? Well, we'd expect the opposite. If increasing pressure favours the right-hand side, then decreasing pressure will favour the left-hand side. So we would expect the opposite. We'd expect it to go from colourless to dark brown, or if it was already in equilibrium, from pale brown to dark brown. But importantly, it would get a darker brown colour because it would now be shifting to the left-hand side and more of that NO2 is going to be produced. The other thing it says, when the temperature is increased by putting the syringe in a beaker of hot water, what colour change do we see? And we see again pale brown to colourless. And that again shows us that it shifts to the right hand side. Now bear with me, because I'm just explaining what the colour change would be if we had been able to watch the demonstration, and I'm very aware that I haven't explained why it favours that side yet. So I don't want you to assume that high pressure always favours the right hand side and high temperature always favours the right hand side, because it doesn't. I'm going to go over how we can work that out in a minute. So if we had increased the temperature, then it would have gone from pale brown to colourless, and again that shows us that it's shifted to the right hand side. So high temperature favours the right hand side, high pressure favours the right hand side, and that means that low pressure would favour the left hand side, and the same, a low temperature would also favour the left hand side. It would do the opposite. If high temperature favours the forward reaction, a low temperature would favour the backwards reaction. So we would again see the opposite colour change. We would see it go from colourless to brown. So we can talk about why. Why did these things happen? And the first thing is, we'll talk about pressure. If we have increased the pressure, then the equilibrium will want to decrease it. Now remember, it's in a closed system, which means that our volume is fixed. The volume of our gas syringe and our conical flask is fixed. It's not getting any bigger, it's not getting any smaller. So if we increase the pressure, the equilibrium will want to decrease the pressure. Now, pressure is caused by the concentration of gas particles in a fixed volume. If you can't change the volume, then all you can change is the number of gas particles. And if we look at our equilibrium, if we look at the equation, well, on the left hand side we've got 2 molecules of NO2, but on the right we've only got 1 molecule of N2O4. So if the equilibrium was trying to shift to lower the pressure because I had increased it, well, if it shifted to the left, it would have twice as many particles, which would increase the pressure, which isn't what it wants to do. It wants to do the opposite. If it shifts to the right, however, it's got half as many molecules of gas, so the pressure would decrease. So by shifting to the right hand side, by favouring the side with the fewer molecules of gas, it can lower the pressure, which is precisely what it wants to do. It wants to do the opposite of what I did. So if I increase the pressure, it will favour the side with the fewest molecules of gas, so that it could then lower the pressure. And then we said that if we decrease the pressure, if we lowered it, we would expect the opposite to happen. And that makes sense, because if we lowered the pressure, the equilibrium will try to increase it, try to do the opposite. Well, which side is going to give it that higher pressure that it wants? The 1 molecule of gas or 2 molecules of gas? Well, it's going to be the 2, isn't it? If you want to increase pressure, you want to have more particles in a fixed volume. So by favouring the left-hand side with the more molecules of gas, it would then increase the pressure. In terms of temperature, we were given a little bit of information here. The reaction is endothermic in the forwards direction. So if it's endothermic in that direction, going from left to right, it must be exothermic in the backwards direction. Now, all we need to remember now is the definitions of endo and exothermic reactions in terms of temperature. So remember, endothermic reactions get colder. You have a temperature decrease in an endothermic reaction, whereas an exothermic reaction gets hotter. It releases energy. It has a positive temperature change. So what we saw was we increased the temperature and it favoured the right hand side. And again, that makes sense because if we've increased the temperature, the equilibrium will try to decrease it. So it's got a choice. It can either favour the endothermic reaction or the exothermic. It can either go from left to right or right to left. And we've increased temperature, so it favours the forwards reaction because in this particular example, the forwards reaction is endothermic, and we know that endothermic reactions decrease temperature, which is the opposite of what I changed. So increasing temperature favoured the right hand side because the forwards reaction was endothermic, which would lower the temperature and counteract the change. Then we did the opposite, we decreased the temperature. Now decreasing the temperature will cause the equilibrium to try and increase it. So again, it's got two choices. It's got the endothermic reaction going forwards, or it's got the exothermic reaction going backwards. And we should remember that exothermic reactions increase in temperature. So it favours the backwards reaction because it's exothermic, which increases the temperature and counteracts my change. So, looking at these 6 and 7, what general rule applies for increasing pressure on an equilibrium reaction? So increasing pressure favours the side with the fewest molecules of gas. Okay, so you're looking out for this state symbol to identify that they're gases, and you're just looking for the number in front of it to tell you how many there are. So there's a 2 there, so that's 2 molecules of NO2. There isn't a number here, so we assume it's 1, which gives us 1 molecule of N2O4. Okay, increasing temperature always favours the endothermic direction. Okay, so increasing temperature favours the endothermic direction, therefore decreasing temperature would favour the exothermic. Increasing pressure favours the side with the fewest molecules of gas, but decreasing pressure would favour the side with the most molecules of gas. And so the only way to determine which side will be favoured, left or right, when we're talking about pressure, is you must have the balanced equation, because you need to know how many molecules of gas are on either side in order to make that decision. And in terms of temperature, you must know which direction is endothermic, which direction is exothermic. Now in this case we were told in the question, but sometimes it won't be written down. Sometimes they will just give you an energy change for the reaction. So perhaps the change in energy in this case was, I don't know, positive 200 kilojoules, just for example. And they might just write it like that next to the equation. When they give you the energy change, we need to remember, number one, if it's positive, that means endothermic. And if it's negative, that means exothermic. And the other thing we need to consider is when they give us an energy change, when we're talking about a dynamic equilibrium, that energy change always refers to the forwards reaction, left to right. So if it had been written like this, we would say, right, that's positive, so that's endothermic, and that is in the forwards direction, meaning that the backwards reaction is exothermic. If that value had been negative, then it's the opposite. It would mean the forward reaction was exothermic, which would mean the backwards reaction was therefore endothermic. So changes to a dynamic equilibrium are all determined by something called Le Chatelier's principle. So Le Chatelier's principle states that an equilibrium system, or dynamic equilibrium system, will always shift to counteract any change in conditions. Now, so as long as you remember that the dynamic equilibrium does not want to change, so it will always do the opposite of what you've done. So if you increase temperature, it will move to decrease temperature. If you increase pressure, it will move to decrease pressure. If you increase the concentration of something on the left-hand side, it will move to decrease the concentration of whatever you've increased on the left-hand side. And fundamentally, it can do two things. It can either shift to the left or it can shift to the right. So we can use Le Chatelier's principle to explain our observations from the demonstration. And I know we didn't actually get to see it, but we did talk about it. So the first thing was, if I just write out the equation quickly, so it was 2NO2 gas going to N2O4 gas. And we knew that this side was brown, this gas was brown, and this one was colourless. So, the other bit of information we had was it told us that it was endothermic in the forwards direction, exothermic in the backwards direction. Now, as soon as you have a balanced equation and you know which one's endo and which one's exo, you now have all the information you could possibly need to predict the effect of changing any conditions. You could predict the effect of changing pressure, the effect of changing temperature, the effect of changing concentration. So we started with, we increased the pressure. That was our first observation. So increasing the pressure caused a color change from brown to colorless. And the reason it did that is because it shifted to the right hand side. So because the equilibrium shifted to the right hand side. So we can explain that. So this is because there are fewer molecules of gas on the right hand side. There are 2 on the left, but there's only 1 on the right. So this is because there are fewer molecules of gas on the right hand side, therefore reducing the pressure, because that's all the equilibrium is trying to do, is trying to counteract our change. We increase the pressure, the equilibrium will reduce the pressure. The other thing we did was we increased the temperature. So increasing temperature also caused a color change from brown to colorless. And for the exact same reason, because the equilibrium has shifted to the right hand side. Now, why did it do that? It's because increasing temperature favors the endothermic reaction, which in this case happens to be the forwards reaction. This is because the forward reaction is endothermic, therefore reducing temperature. And again, we increase temperature, so the equilibrium reduced that temperature. Now, you could do the opposite. If we decrease the pressure, it would favor the left-hand side, because there's more molecules of gas on the left-hand side, therefore increasing the pressure. And if we were to decrease the temperature, it would favor the backwards reaction, because the backwards reaction is exothermic, therefore increasing temperature. In this graph, we can see yield of ammonia. Now, the word yield basically just means how much. So it's saying how much ammonia is being produced in this reaction. So this is the Haber process, which is the industrial process we use to produce ammonia. And it's a dynamic equilibrium. So nitrogen gas reacts with hydrogen gas to produce ammonia. And it's dynamic equilibrium, so as quickly as the nitrogen and hydrogen are combining to produce ammonia, the ammonia is breaking down to produce nitrogen and hydrogen. So we really want the ammonia. So we want our dynamic equilibrium to favour the right-hand side. So we can use Le Chatelier's principle to our advantage. And if we were to change the temperature and the pressure, we can manipulate this equilibrium so that it shifts to the right hand side and produces more ammonia, giving us a higher yield of ammonia. So here we have a variety of different temperatures. So we can see that the lower the temperature, the higher the yield. So at 350 degrees we get a 70% yield, but at 550 degrees we get about a 20% yield. So low temperature gives us a higher yield. So when temperature increases, the yield decreases, or the yield of ammonia, I should say. So in terms of how much ammonia we get, we want a low temperature. And when pressure increases, so we can see as pressure is increasing here on our x-axis, we can see that the yield is increasing. So if you pick any one of these curves, you can see clearly they are all increasing with pressure. So when pressure increases, the yield of ammonia increases. Now, we can explain why that happens. So if I just redraw it so that we have nitrogen, hydrogen producing ammonia. Now, what you need to know is that it is exothermic in the forwards direction, which means it's endothermic in the backwards direction. So we've said that when temperature increases, the yield of ammonia decreases. Well, that's because when we increase temperature, it favours the endothermic reaction to decrease the temperature. And the endothermic reaction is the backwards reaction, which means more ammonia is going to be broken down into nitrogen and hydrogen. So that makes sense. When pressure increases, the yield of ammonia increases. And if you remember, when we're talking about pressure, we're talking about the total number of gas molecules. So increasing the pressure will favour the side with the fewest molecules of gas. So let's look at how many we have. So on this side, we have 1 molecule of nitrogen and 3 molecules of hydrogen. So we have 4 in total. And on the right, we just have 2 molecules of ammonia. So a high pressure would favour the right hand side because it's got fewer molecules of gas, which is exactly what we're seeing. The higher the pressure, the higher the yield. So can you explain why more ammonia is formed at low temperatures? So the forwards reaction is exothermic, therefore is favoured at low temperatures, because if we've lowered the temperature, the equilibrium will try to increase it, and it will do that by favouring the exothermic reaction. So the forwards reaction is exothermic, therefore is favoured at low temperature, which increases yield of ammonia? And can you explain why more ammonia is formed at high pressure? So there are fewer molecules of gas on the right hand side. Therefore, the right hand side is favoured at high pressure, which increases the yield of ammonia. So finally, the Haber process uses a temperature of 450 degrees, a pressure of 200 atmospheres, and an iron catalyst. Explain why these are the ideal conditions. So what we now need to talk about is yield and rate. So we're sort of going back to when we're talking about rate of reaction. So in terms of yield, in terms of how much ammonia we can get, we've already established is that low temperatures will increase yield of ammonia. And we've also established that high pressures will increase yield of ammonia. So we've gotten both those bits of information from the graph, because that's exactly what the graph told us. It said that the lower the temperature, the higher the yield, the higher the pressure, the higher the yield. But also looking at the balanced equation, we can also work out that a high pressure would favour the right hand side, giving us more ammonia, and a low temperature would also favour the right hand side, giving us more ammonia. But it's not always just about how much we get, it's also about how quickly. So let's think about these changes in terms of the rate. If I wanted the rate of reaction to be fast, I would actually want a high temperature. So a high temperature will increase the rate of reaction, the rate of production. And that's going back to collision theory. If we increase the temperature, we're increasing the kinetic energy that particles have. They're going to collide more frequently and with more energy. And in terms of pressure on the rate, a high pressure will also increase the rate of reaction, because you're going to then have more particles in a fixed volume, increasing the frequency of collisions. And the other thing we spoke about was a catalyst. Now, it's important to remember that catalysts do not have any effect on position of equilibrium. So if it ever asks the effect of a catalyst on the position of an equilibrium, it has no effect. It only affects the rate. So a catalyst increases rate of reaction. So in red, I've got the changing conditions and the effect they have on the rate, and in black, I've got the effect they have on the yield. So let's look at the values we have. So they've gone for a temperature of 450 degrees. Now that is not a low temperature. So it's going to give us quite a low yield, but it will give us a fast rate. 200 atmospheres is a high pressure. That's 200 times more than the atmospheric pressure. The pressure that you feel right now in the room is 1 atmosphere. So it's 200 times more pressurized than the air. So high pressure will give us a high yield. High pressure also gives us a high rate, so it makes sense that we use a high pressure. And the catalyst doesn't have any effect on the yield, but it does also increase the rate. So these conditions that they've chosen they are a compromise. So these conditions are a compromise between yield of ammonia, so how much is produced, and rate of production. Finally, we're just going to summarize the effect of the conditions you can change on a dynamic equilibrium. Now remember, the three things you can change are temperature, pressure, concentration. The other thing you might be asked about is a catalyst, but remember, catalysts don't have any effect on the position of equilibrium. So we'll start with temperature. Increasing temperature will favor the endothermic reaction. Decreasing temperature will favor the exothermic reaction. Okay, and the reason it does that, so that increasing temperature will favor the endothermic reaction because the endothermic reaction decreases the temperature, so to counteract the change. So I'm just going to add that, to counter the change. And the same with decreasing temperature. Decreasing temperature favors the exothermic because that would increase the temperature and therefore counter the change. In terms of pressure, increasing pressure will favor the side with the fewest molecules of gas, and decreasing the pressure will favor the side with the most moles of gas. And again, to counter the change. To counter the change. So increasing pressure will favor the side with the fewest molecules because then there will be fewer particles in a fixed volume and the pressure will decrease. If I were to decrease the pressure, it favors the side with the most molecules of gas because then that would increase the particles in a fixed volume and therefore increase the pressure. Now concentration is a little bit different. So increasing concentration will favor the opposite side. So for example, if I increase the concentration of the left, it will favor the right. If I increase the concentration of the right, it will favor the left to counter the change. And again, if I decrease the concentration, it will favor the same side. So if I were to decrease the left-hand side, it will favor the left-hand side. If I were to decrease the concentration on the right-hand side, it will favor the right-hand side to counter the change. So all of these changes in conditions result in a shift in equilibrium in order to counter the change. So if I've increased temperature, it will shift to decrease it. If I increase pressure, it will shift to decrease it. If I increase concentration, it will shift to decrease it. So as long as you can work out whether it's exo or endothermic in the forwards and backwards reaction, as long as you can work out how many moles of gas or molecules of gas there are on the left or the right, then you will be able to work out the effect of changing conditions on that equilibrium. Here we are looking at a dynamic equilibrium system that's been set up between two different species of cobalt. We have hydrated cobalt and cobalt chloride. Now, this is a reversible reaction, so it occurs forwards and backwards, and it's in dynamic equilibrium, which means that both reactions are occurring at the exact same time at the exact same rate. So what we can see here in each one of these boiling tubes is a reaction that's occurring where the hydrated cobalt is combining with the chloride ions to form cobalt chloride and water, and at the exact same time and rate the opposite is occurring. The cobalt chloride and the water are forming hydrated cobalt and chloride ions. And because both reactions are occurring at the same time at the same rate, they basically cancel each other out. So the reaction appears to be doing nothing. Okay, it's not going forwards more than it's going backwards. Both reactions at the same rate. So this hydrated cobalt is pink, and this cobalt chloride is blue. And what we're seeing, this sort of purpley colour, is sort of a mix of the two, because obviously both reactions are occurring. And dynamic equilibrium will shift position to counteract any change in conditions, and that's stated by Le Chatelier's principle. So if I were to increase the temperature of a dynamic equilibrium, it will decrease the temperature. If I were to increase the pressure, it would try to decrease the pressure. If I were to increase the concentration of something, it would try to decrease it. And if I did the opposite, if I tried to decrease the concentration of something, it would try to increase it. So the dynamic equilibrium is always going to shift in order to counteract the change. So whatever change in conditions you impose on the system, it will shift to do the opposite. And by shift, I mean it can only do one of two things. It can either favour the forwards reaction, or it can favour the backwards reaction. They're the two choices any dynamic equilibrium system have. So all you've got to work out is which reaction would counteract the conditions. So we don't know really anything about this system at the moment. Number one, we're talking about aqueous solutions, so pressure is not going to be a factor here, because pressure is only going to apply to equilibrium systems that have gases. But we can look at the effect of concentration and the effect of temperature. So I'm going to start with concentration. So I'm going to increase the concentration of the chloride ions. So we're going to keep this one here with no change. We're going to leave it as it is so we can use it to compare. So I want to increase the concentration of the chloride ions, which are over here on the left-hand side. So if I were to increase that, the dynamic equilibrium will want to do the opposite. It will want to decrease it. And the only way it can decrease the concentration of those chloride ions, if I increase them, is to use them up by favouring the forwards reaction, using them up and forming cobalt chloride. So we would expect, if I increase the concentration of chloride ions, the equilibrium will shift to the right to counteract that change, and what we will see is it going more blue. So let's see if that happens. Let's add some concentrated hydrochloric acid so we can add some chloride ions, and you can see straight away that it has gone blue. So it has shifted to the right hand side, which is what we expected. Let's look at the water then. If I increase the concentration of the water, which is here on the right hand side, and I increase that, my equilibrium will want to do the opposite. It will want to decrease it. So how could it do that? Well, it could favour the backwards reaction and use that water up. So if I add some water to increase the concentration of the water, you should see a subtle change, but it has turned more pink. If you compare that to the original starting solution, it is more pink than purple. So we can see that by increasing the concentration of the water, the equilibrium has shifted to the left-hand side, the backwards reaction, to use up that water so that the concentration remains the same. The other thing we can look at is the effect of temperature. Now, one of these reactions, the forward reaction or the backward reaction, one of them is going to be exothermic. The other is going to be endothermic. So if I increase the temperature, then the dynamic equilibrium will want to do the opposite. It will want to decrease the temperature. So it will favour whichever one of these is endothermic. And if I did the opposite, if I cooled it down, if I reduced the temperature, again it would shift
in order to increase that temperature. So it would favour the exothermic reaction. Now we don't know which is which yet, but we can quite easily find out. So if I increase the temperature first, so if I take my equilibrium system and I heat it gently over a Bunsen flame, we should start to see a colour change. So just heating it very, very gently over that Bunsen flame, and immediately it's gone a dark blue colour. We can take this other one, we can decrease temperature. If we stick it in an ice bath, which I just have here, and we'll just leave it there for a few moments. So the fact that increasing the temperature turned it blue told us that it favoured the right hand side. Okay, the fact that it turned blue told us that it favoured the forward reaction. Now, increasing temperature will always favour the endothermic reaction. So what we now know is that this forward reaction is the endothermic reaction, which means that the opposite must be exothermic. So what we are going to now expect to see in the lowered temperature is we should see that it favours the left-hand side, and it should go a lighter shade of pink. So we'll just have a quick look at it now. It's just been there a few moments. It's obviously a little bit slower, but we should see, hopefully, there is a lighter shade of pink than the original. If we leave it longer, it will go lighter shades of pink. So if we were talking about a gas system where we had reactants or products that are gases, the same principles apply. If I were to increase the pressure, then the equilibrium will shift forwards or backwards in order to decrease that pressure. Or if I decrease the pressure, it will shift forwards or backwards to increase it.